let's continue working some integration by parts problems. The first one is integral of x times natural log of x plus 1 dx. So you could do this by integration by parts, and there's nothing wrong with that. But what I would like to do is do a substitution problem first, and maybe that'll make our lives a little easier. You don't have to do it this way, but this is how, if I were doing it, I would approach it. I would say, okay, well, I'm going to say that I'm going to use the word t. Normally we'd use a u substitution, but we're already using u in dv, so I don't want to confuse that. So I'm going to say t equals x plus 1. And rewriting, that also makes x equal to t minus 1. So dx equals dt. So that's simple enough. So if we rewrite this, we then get t minus 1 times natural log of t dt. Alright, well, the reason why I want to do this is because then I can translate this to two separate integrals. T natural log of t dt minus natural log of t dt. The reason why I like to do this is because this is kind of a standard, well-known, we covered this in a previous video, that's a sort of well-established integral. So I'm not going to say we can directly integrate it, but if you have a good familiarity with the tables, you can jump straight to it without having to really go through the integration by parts piece of it. But instead, we can focus on this piece for integration by parts. So this piece, so we'll come back to this, but this piece here, what we'll do is we'll say, all right, u is natural log of t, dv is t dt, du is 1 over t dt, and v is 1/2 t squared. So then we can use our formula. We say u dv is equal to uv minus integral v du. It's a v. So we can fill this out. So u dv is here. So that's t natural log t dt is equal to uv, so 1/2 t squared natural log of t minus v du, so minus v du. Now t squared times 1 over t, you just get a cancellation of one of the t's, so that's 1/2 t dt. So that's 1/2 t squared natural log t minus 1/4 t squared. But we have all this piece here. So we would put a plus c here, but let's finish this out. So now I need to bring that down. Well, the antiderivative of natural log of t is t natural log of t minus t. That's just the standard antiderivative here. So that's 1, and so then we get a plus c. So 1/2 t squared natural log of t minus 1/4 t squared minus t natural log of t plus t plus c. But again, we didn't start in t's, we started in x's, so we get 1/2 x plus 1 squared natural log of x plus 1 minus 1/4 x plus 1 squared minus x plus 1 natural log of x plus 1 plus x plus 1 plus c. So all that. Technically, what you'd probably see in some book is 1 plus c would be absorbed, so you just have plus x plus c. You might actually see a lot different of an answer because when you multiply this out, you're going to get another constant as well. So you could, the actual thing you see, if you were to look this up in some sort of table, might look a lot different, but it would be equivalent. And if you took its derivative, you'd get back to that. So this is kind of an ugly answer, but in my mind, it's a more straightforward process. And generally speaking, a more straightforward process with an uglier answer is going to be preferable to an uglier process with a cleaner answer. You can clean up answers on the back end. It's hard to clean up processes if things go wrong. So do yourself a favor and walk through the easy process as much as you can. Alright, so I had picked a pretty poor idea to do. I was trying to do something similar to the way I did over here with a substitution, and while that probably would have worked, it was intended to make things simpler, but it actually made it more complicated. So instead of going through that process and sort of painfully walking you through it, I'm going to go back to the original process and kind of do it in my mind, a little less elegant way, but probably is still going to get you there. So in this particular case, we have kind of a nasty expression. We have x cubed e to the x squared over x squared plus 1 squared dx. So what I like to do is I like to rewrite this in things that make sense, that are a little more convenient. So one thing that's helpful to do is to rewrite this in terms of two functions. One of them that you know you can integrate. Even if you don't know exactly what the antiderivative is directly, if you look at it and go, okay, I can do that, pull that piece out. So I'm going to rewrite this as x So what I did is I pulled one of the x's out over this. So now I have two pieces. The reason I want to do this is if I look at this, I say, oh, I can take the antiderivative of that. I'll have to use a substitution, but I can do it. So I say, all right, u is going to be the thing I can't take the antiderivative of very easily. And dv is x over x squared plus 1 squared dx. So hopefully, if you have trouble figuring what that out is, set that up as an integral, take your u sub or t sub or whatever to be x squared plus 1, and then go from there, and you should be able to get that. So you should get negative 1/2 times 1 over x squared plus 1 when you take the antiderivative. And the derivative of this is going to be a little more complicated. So hopefully that doesn't scare you too much. It's kind of a big, nasty monster. So going through, we now have a v and a du. So I can use my formula here and plug in. I say, all right, sorry, no integral symbol there. So I get uv, so negative 1/2 squared e to the x squared minus v du, so minus negative 1/2 du. So you get kind of that monster there. So you might ask yourself, okay, how do I do this? How do I make this work? Well, we're going to have to be a little clever with our algebra here. This is negative 1/2 So I have a minus minus here, so I'm going to rewrite that as a plus. And then I'm going to factor out what's common. So what's common to each of these? I can factor, there's a 2, an x, and an e to the x squared. That's common to both of those. So I get 2x e to the x squared. And what's left over? Well, 1 here, because it was everything. And then this was an x cubed. So if I pull this out, what's left over is 1 plus x squared dx. So now I have, oh, this was a 1/2 as well. So now the 1/2 cancels with the 2, and the x squared plus 1's cancel. So I'm actually left with negative 1/2 with those canceled, I have integral x times e to the x squared dx. Now, in this particular case, you'd use a u substitution here. You take u to be x squared, so du is 2x dx. In the interest of board space, I'm not going to go through that entire u substitution. Hopefully you feel comfortable with that. So you end up with negative 1/2 x squared e to the x squared for x squared plus 1 plus 1/2 e to the x squared plus an arbitrary constant. Let me check my cheat sheet here. Okay, and so that is correct. That's a nasty little bugger, right? That's not exactly straightforward. And the key to this, as I've said before, is algebra skills. Without algebra skills, if you didn't have the algebra skills here, you might have tried to separate that into 2 separate integrals and do more integration by parts. And you might have gotten there, but you would have worked a lot harder than if you'd used your algebra skills here to simplify. So always look for ways to simplify. Never work harder than you have to.